Association of Victoria, on behalf of the MAB and Melbourne Museum, our wonderful sponsor, I welcome you to this, the last of the 2012 public lecture series. Now these lectures have been greeted with great acclaim during the year, but there have been a couple of controversies. Last month people will be aware of the fact that Senator Nick Xenophon was somewhat concerned that we might be teaching young children how to win at the casino. Well, I have to bring another scandal, ladies and gentlemen, to your attention today. I had always thought that Marty Ross and Burkhard Polster were pure mathematicians. That they only thought pure thoughts, that they only explored the abstract. But I have discovered, ladies and gentlemen, that they are nothing but cheap, applied mathematicians. Yes, ladies and gentlemen, when they published their book, instead of using maths goes to the movies, thereby limiting their market to Australia, they've done their applied arithmetic and worked out they can sell more books by saying math and pretending they're from America. This, ladies and gentlemen, is a scandal. It's, however, quite applicable that playing around with maths is something that they've done in a book about Hollywood. And maths goes to the movies. And today, you're going to get a taster from the maths master. Please make him welcome, Burkhard Polster.
Right. Thank you all for coming today. So, as Simon said, it's our last lecture for the year. It's been 6 years of lectures so far, I think. Is it 6, Martin?
10.
10. Or is it 11 actually? I think
11, yes.
Might be 11.
Yeah.
You lose track of these things. Okay, so 11th year of lectures in the Melbourne Museum, and hopefully we'll be back next year for 12th year. So today we'll be talking about all sorts of stuff, but we've never talked actually about Hollywood maths, mathematics in the movies. So it's a first for the museum. We've talked about it for other occasions, but not in the museum. All right, now today I actually want to do this in a slightly different way. Usually what we do is we talk about something, and then at the end we say, well, go here and there if you want to know more. So I'm going to start at the spot where you should go when you finish with this, and explore more. And that's Marty and my webpage. So just in case you haven't been to any of the other talks, this is Marty. He lurks over there with the camera. So he's the man with the pizza. Oh yeah. And I'm the one with the chainsaw, obviously. And Hollywood maths didn't start in Hollywood. It actually started here in Melbourne. And it started about, well, 11 years ago. That was the time when I met Marty for the first time. He was giving a lecture at Monash University, and he did something that I hadn't seen before. He used a couple of movie clips from really obscure movies, really, that had some maths in it, to illustrate some really good points. So those clips really fitted in very, very well. And I was very impressed by this. And later on we got to talk, and actually since then we have been doing lots of things together. So for example, I mean, if you've been here, if you haven't been here, you have to go there. So it's not, and that's the first thing you have to know, it's not QuedCat, it's QED Cat. Okay? And this is the QED Cat here, this is the QED Cat, our logo. Very important, makes an appearance later on in the talk, so remember the QED Cat. So one thing we do, or have been doing for 6 years, I think, is we write an article for the education section of the Age, and that pretty much comes out every Monday. And for the last 70 or so articles, we've actually matched that with a movie clip. So some clip that has something to do with what we're talking about that given week. And those go up pretty much at the same time, so you may have seen them. You've definitely seen them if you're on our list. So they're listed here. And well, just in general, I mean, for 10 years or 11 years now, we've been really serious about collecting everything that has anything remotely to do with mathematics in the movies. And so the master list you can find here. So if you're asking about maths in the movies, or Hollywood maths, it's not in Hollywood, it's right here. Right here, Hollywood maths. And we'll have a quick look at that spot where Hollywood maths resides in a second. And this is the book that Simon mentioned. So that's another spot that finally appeared. So again, it's been a project for ages, and finally in August it's come out. So these are the spots that you have to visit if you're interested in anything remotely to do with movie maths. There's a list of clips, about 70 of them. There's the master list, and there might even be the book. There's even a couple of chapters preview on Google Books if you want to just check it out. Okay, so here's the mathematical movie database. It's actually a very straightforward page. Just a bit of a blurb, give it some links here. I'll show you the first page here. It's a huge list, and it's so huge that it's actually easy to get lost there. So what we've done is we've taken a couple of movies out that everybody who's remotely interested in mathematics and movies should see. And here's just a list. So I'm going to get cut off a little bit. So there's, for example, Beautiful Mind that you might be familiar. Anybody seen The Beautiful Mind? Everybody seen The Beautiful Mind? Anybody not seen The Beautiful Mind? Okay, so you're going to go home and see The Beautiful Mind. It's a must. So it's with Russell Crowe. He's almost an Australian, right? And so this almost Australian here is playing a genius mathematician, John Nash. And there's another one that probably everybody has seen. Good Will Hunting. Everybody seen Good Will Hunting? Yeah? Okay. Anybody's not seen Good Will Hunting? The same. But you really have some catching up to do here. So obviously you're interested in maths and interested in movies, so you all go home and check out this page and watch all the movies. Right? Now, okay, so the rest of you are on track, but you probably haven't seen some of these movies. For example, I'll just pick on 3 of them. So there's The Bank, right up on top. So this is an Australian movie about a mathematical prodigy who has a bone to pick with a bank, and he uses fractals and Mandelbrot sets and all kinds of stuff to predict the stock market. Very, very nice movie. Then there's a Disney movie entirely dedicated to mathematics. So it's Donald Duck having an adventure in Mathmagicland. Has anybody seen Mathmagicland?
Yes, yes, yes.
So those of you who have seen Mathmagicland, how many of you are teachers? Ah, right. So it's actually quite a well-known movie in the teaching community. For a long time it's been completely inaccessible. So actually Martin and I, we've been showing this movie for years and years, but we only showed 60mm copy. Recently it's actually become available on DVD. It's again worthwhile to check it out. So there was Fantasia, kind of doing classical music, and there's Donald Mathmagicland doing the same for mathematics. And then there's another one, and I'll be really surprised if anybody's heard about this one, Fermat's Last Tango. Anybody seen that one? Oh, there's one. That's actually a mathematical musical. To our knowledge, it's the only mathematical musical. Well, there might be another one, but we haven't been able to track it down. And I'm going to actually show a clip later on. It's just a curiosity. And we could talk about any of the other movies. They're all great here, and you should all check them out. So just quickly, second page. Here gets serious. It's a complete list. And I'll just show you what you can actually do with this. And especially if you're teachers here, this might be a place for you to go if you're looking for something specific in the movie. So for example, if you're looking for Pythagoras in the Pythagoras theorem in the movies, we've got a bit of a blurb here for every single entry, and we usually weave in keywords. It's just one big page, there's no picture, so it loads very quickly, so you just type in Pythagoras and click, 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 and you maybe get like 20 entries with movie clips having Pythagoras in it. We've got a bit of a rating here. It's a very kind of personal rating. It's got nothing to do with age or anything. It's just how much good maths is in there, and good maths is defined by whatever Martin and I think good maths is. So for example, here we've got a 3-star rating for, you can actually not see what it is, it's 21, it's Kevin Spacey, where he beats the casinos by counting cards. Probably quite a few of you have seen this one. And there's also a link to IMDb. This is called the Mathematical Movie Database. Now this is the International Movie Database, which is even bigger than our database. And here you can find like all the information about any movie that we're listing here, so like actors and directors and reviews, all kinds of other things. And for some of these, we've also got clips. And so the links here that you might see, they either link to that list that I mentioned before, those 70 clips, or there's another really, really huge one compiled at Harvard University by Oliver Knill. And he's got about 150 sitting there. So you can just spend maybe a couple of hours just clicking through those links when you get home and have a bit of fun. All right, so that's basically what's there. And just to give you an idea of how big this list is, I'm just going to scroll now. So we're on page 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 22, 23, 24, 25, 26, 27, 28, 29, 30. And now come the TV episodes, right? So there's a lot there, right? There's a lot there, but it's all in one place and it loads very quickly. And if you're actually looking for something, it's very easy to navigate. All right, now what am I going to do with all this stuff? Well, Marty and I, we're really interested in not only collecting these things, but actually using them in some way. So we are teachers, we're teaching at university. So we're using these clips like on a daily basis. I pretty much, any lecture I give, I put some movie clip in. All right, now let's just jump into it and do something with it. Let's do a bit of revision, okay? Revision of some basic mathematics. So kids, just in case there are any questions here and you know the answers, you can always jump in and see whether you get in earlier than the actors themselves.
Right, Warwick, let's try again, shall we? This is called adding. If I have 2 beans, and then I add 2 more beans, what do I have?
Some beans.
Yes and no. Let's try again, shall we? I have 2 beans, then I add 2 more beans. What does that make?
A very small casserole.
Baldrick, the 8 creatures of the Indus have mastered this. Now try again. 1, 2, 3, 4. So how many are there?
3.
What?
And that one.
3 and that one. So if I add that one to the 3, what will I have?
Oh, some beans.
I could have videotaped myself here at university. I mean, my conversation with students often like this. This is real life. But it's also a revision of the editing. Now, let's move up a little bit. So let's do a little bit of something harder. Everybody's done this before. Multiplication, okay? Multiplication. Okay, let's have a look here. So we're going to multiply. A bit of a hard thing. 7 times 13, okay? So that's a good one.
Hey, wait a minute. You owe me back room rent.
Now, don't get excited. How much is it?
You owe me 13 weeks at $7 a week.
Tidy sum, isn't it? Pardon me just a minute.
Sure.
Lou. Here's $28. $28? Give him that old routine of ours, 7 into 28, 13 times.
Oh,
Hey, give me the crayon. Oh, yeah. And do it right this time. Oh, it works. Make it snappy. Okay. Mr. Landlord.
Yeah?
What are you smoking, an army blanket?
Never mind about that. You owe me room rent.
All right, here's $28.
$28, fine. Just a minute. You owe me 13 weeks at $7 a week, and that happens to be a lot more than $28.
Well, that comes to $28.
Did you go to school?
Yes, sir.
Do you mean to say that you can prove that 7 times 13 is 28?
Well, it's got to be. Certainly it is, because Mr. Rabbit and I, that's $28. That's what you get.
If you can prove it, I'll tell you what I'll do. I will give you the room rent for nothing.
You will?
But if you don't prove it, you owe me double the back room. Is it a deal?
That's a deal.
Okay.
Do you happen to have any Crayola on there?
Crayola?
Never mind. I got it.
Oh, you have?
I got the Crayola. 7 into 28 is going to come out 13.
That's your way.
That's my way. And it's got to come out right. Now, first, I put down a 7.
Right.
Now, I'm going to divide the 7 into 28.
Yeah.
I put a 28 there.
Okay.
Isn't that cute? Now, here we go. 7 into 2. 7 will not go into 2.
It will not.
That's a very big 7 to push into that little bit of 2. We ain't going to hurt that little 2, are we?
Of course you will.
So we take the 2, open your hand,
Yes.
and I put that 2 right there for safekeeping. But don't drop it and don't lose it. Now, 7 into 8.
Once.
Once, I put the 1 over here, 1 over there. Now, we're going to carry the 7 because it's very big and it's getting heavy on my shoulders, and I'm going to drop the 7 under there. Now, 7 from 8
Is 1.
is 1. I put the 1 down there. Now comes. Would you mind opening up your palm of your hand, please? I would like to use that 2. Open it up. Give me that 2. You've had it long enough. I'm going to put that 2 right there. Now, 7 into 21.
3 times.
That's right. 7 into 28. 13.
Wait a minute. You have to prove this even better than that. You can prove it very easily by multiplication.
You mean you want me to multiply it?
No, not multiply, multiply. Multiply.
All right. Multiply it.
7 times 13 is 28. Go ahead.
Now, first, we've got to put down a 13, right?
Right.
There's a 13.
Times 7.
Times 7.
Right.
7 weeks times 13, right? 7 times 3.
21.
21. 7 times 1.
7.
7. 7 and 1. And 2.
Now, wait a minute. I'm still not convinced. There's one sure way of proving this. One sure way, and that's by addition.
You want me to addition it up?
I want you to put 13 7 times on that wall and then draw a line and add them up.
You want me to put down 13 7 times?
That's right.
Let's cut them out, right? There's 1,
1,
2,
2,
3,
3,
4,
4,
5,
5,
6,
6,
7.
Wait a minute. What's the idea of spreading them out like that?
Well, it looks like a flock of seagulls going to hit the electric poles. Now we're going to add them up, right?
All right, go ahead.
Here we go. 3, 6,
Wait a
9.
minute. Let me do the adding this time.
Good. Come out right.
Well,
3, 6, and 9.
Just a minute. I will do the adding. Then there'll be no mistake.
Yeah?
All right? $28 here. All right?
Sure.
Now,
Go ahead. If you had enough questions.
3, 6, 9, 12, 15, 18, 21.
22, 23, 24, 25, 26, 27, 28.
Anybody here who doesn't believe now that 7 times 13 is 28? You think there's anything else? There might still be some people who doubt this, right? There's still some people who doubt that 7 times 13 is 28? Well, if you do, you can watch this clip here, where they do the same thing, it's basically the same people. Or you can watch this clip, where they do the same thing. Or you can watch this clip, where somebody else does the same thing. Now let's see whether you can actually recognize any of those people here. We'll just do a quick one.
So there were 7 of us, and the check came to $28, so I figured out I owe you $4.
No, you don't. You owe me $13.
13.
Yeah.
Anybody recognize anybody here? Yeah, this is actually Michael Jackson when he was doing a maths routine. It's quite rare. I think Martin paid $80 for it. For some pirate copy of somewhere. All right, but that's not the only thing you can do. You can actually do a whole multiplication table. So all these things, all these things, if you want to learn them, you can basically apply the same techniques that have just been demonstrated to you. And with basically the same arguments, you can show that 3 times 17 is 24, 4 times 15 is 24, 5 times 14 is 25. It's amazing, And just checking, for example, just the addition part here with 24, this one here. So we basically need to do 3 times 17, and we do 7, 14, 21, 22, 23, 24. Works, right? Or here, 14 5 times, 4, 8, 12, 16, 20, 21, 22, 23, 24, 25. It's perfect. And all the other ones work too, so this is really advanced stuff. Okay, now, as I said, 800 just movies on our list. There's a huge backlog, actually. And just in case you watch a movie and see any maths, I have to say this, tell us about it. Chances are we probably know about it already. It's just not been put up on the web, but tell us about it anyway. Now, here's a good idea. I mean, kids really like watching movies. Have you noticed that? They really like it. Now, we've got 800 clips here about maths. And so kids like to watch movies. Sometimes they don't want to do maths. So what if we just put them in front of the TV and play those 800 clips? What are they going to learn, right? Well, they're going to learn, well, but this was clearly comedy, right? So what we just watched is clearly comedy. So, you know, you can use this for teaching maths. But let's just do some serious maths in movies. So, for example, here's something from Star Trek, where Captain Kirk, a graduate of Starfleet Academy, is applying some maths.
Ready, Mr. Spock?
Affirmative, Captain.
Gentlemen, this computer has an auditory sensor. It can, in effect, hear sounds. By installing a booster, we can increase that capability on the order of 1 to the 4th power.
That is very impressive. 1 to the 4th power. Okay, here we've got another one. Now this one, see whether you can recognize the person who's acting. He is actually he's a maths teacher. So he's a maths teacher teaching some geometry. We've had a bit of an accident, but you don't really see this in this scene. So we've actually had half a face burn off. That's why the movie's called Man Without a Face.
Draw a circle. ABC. Draw within it any straight line, AB. Now bisect AB at D and draw a straight line DC at right angles to AB. So far, no mistake. Okay. Any other straight line? AC, bisect AC, and you get the center of your circle.
Well, he actually didn't get an Oscar for this movie, he got an Oscar for Braveheart, right? But again, it's a multi-million-dollar production, and well, obviously, I mean, just in case you're not so clued up on these things, there's a bit of a problem here with this right angle that he's doing. Right? If it wasn't right angle, it would actually be right. So if you actually put the right angle in like this, then you're the true center of the circle, actually here. All right. Pi. Let's learn about pi. Where do you go to learn something about pi? Well, you go to the movie Pi. Right? This is the title sequence of the movie Pi. I hope this actually comes out. So what you're supposed to see now, and I'm not sure whether this is going to happen, but there's going to be digits of pi rolling up the screen, thousands and thousands and thousands of them. So if you watch closely, you can probably learn, the first 100,000 digits of pi. So you have to watch closely now. How's the memorization going? Now, even if you missed something, here's actually not... so how far did you get? First couple thousand? Okay. So there's pi, right? 3.141926535897993, and a couple of dots. Well, there's a bit missing there at the end. Goes on like this. Now, if you actually compare what they've got here with what I've got up there, you'll find that it's correct up to this point here. And then all the other digits are wrong. Well, some of them might be right by accident. But if you actually have a really close look, I did. I had a really close look. There's lots of, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And I mean, there is actually 1, 2, 3, 4, 5, 6, 7, 8, 9 in pi, but just not like this. Anyway. So there's actually somebody who sat down and typed those 100,000 digits, I think. And you would think it's actually a lot easier to just download the correct decimal expansion off the web somewhere. But even in 1998, that was available. All right, now pi I mean, the movies really have problems with pi. I mean, basically, anytime you see pi in the movies, well, let's have a look. So this is, for example, Donald in Mathematic Land. There's a pi creature. So one of the first creatures that Donald meets when he's exploring Mathematic Land. And the pi creature is reciting, it's about to recite pi, and it gets it right about there. So just listen to what it has to say, okay? Just go through with it.
Pi is equal to 3.141592653589747, etc., etc., etc.
Oh, well, close. Nobody noticed. Except for Marty and me, seriously. I mean, this has been around since 1959, and I think I've never seen anybody mention that anything's wrong there. So it's not that bad a mistake. Okay, so there's another one here. Virgin suicides. There's a huge pi here. And it's correct up to here. And the winner is... Well, it's even got the pi wrong anyway. Now, where do you actually have to go to get real good mathematics? Well, you go your kids watching all these things and they're learning about pi, and it's wrong. So what do you actually have to watch to get pi correctly? Well, The Simpsons. So The Simpsons, if you happen to watch The Simpsons, pretty much any maths you see there is correct. It's pretty amazing. So let's just have a look here. There's some girls going to recite pi again. It's a school for the gifted, right? We've got a lot of gifted students in Melbourne, so they all have to watch The Simpsons for mathematics. Actually, our list doesn't have anything or very little about The Simpsons. There's specialized lists about The Simpsons. Have been compiled, like every single bit of mathematics you can find on the web, listed on a separate web page. And there's a couple of other TV series that have attracted similar attention by other people. For example, Numbers has a separate list, and Futurama also has a separate list. So all these series have lots and lots of mathematics. All right. Now, Marty and I, as I said, we're teaching with this stuff. I just want to give you two examples that you can actually use. For example, if you're a teacher in the audience and you want to use some clips for teaching, I will just give you two examples. So here's one for the secondary school, maybe. It's a pretty funny clip. So, I mean, you show this to the kids and they really love it.
If Joe can paint a house in 3 hours, and Sam can paint the same house in 5 hours, how long does it take for them to do it together?
Wait a minute. You never said this was a word problem. Scales! Get over here.
What's up, man?
If I can paint a house in 3 hours, and you can paint it in 5, how long will it take us to paint it together? Lonnie! It takes me 3 hours to paint a house, it takes you 5. How long to do it together? What color paint?
It's simple. 5 times 3. So that's 15. No. Look, it takes 8 hours. 5 plus 3.
That's 8. Oh, man, that's not right. Check it out. There's 1, 2 of them, so it only takes 4 hours. I should know this. My uncle's a painter.
Why don't they just get a house that's already painted?
You know, maybe there is no answer. Maybe it's one of those trick questions. You ever think of that?
I don't know, I mean, 8 sounds good to me.
But wait, there's 2 of them. Come on, there's 2 of them.
Fellas. The chalk, if you please. Thank you.
So you stop here and then you ask. Well, what is that? We've got a couple of options here, right? So we've got 15 and we've got 18 and we've got 4. And so what do you think? What do you think? Any of those any good? No? You don't like those answers? Well, I mean, you'd be surprised. I mean, I give this to maybe year 10 classes, and hardly anybody can do this. Seriously. Even if you know, discuss it for quite a while, this is a question that hardly anybody can do. I haven't tried out specialist math yet. Yeah, but they would be expecting some calculus approach, so maybe they'd also fail. I don't know. Okay, anyway, so has anybody got an answer for me? I mean, can it possibly be, or can anybody tell me why it can't be 8? Like just a simple argument why it can't be 8. That's right, yeah. So if one guy can do it in 3 hours, and you add another person to it, it should take less time than 3 hours. None of these numbers here is you know, less than 3 hours, so none of them can be right. Okay? Now there's various ways of thinking about it. I'll just show you mine, and you can think along, and if you know the answer, you can just jump ahead and shout the answer, and this is what it is. Okay? So I think about it in terms of speed. Okay? So if Joe paints one house in 3 hours, so his speed is 1/3 house per hour. That's what he does. And what about Sam? How fast does he paint? 1/5 of a house per hour, right? So okay, so if they now sitting there together and painting away, and say for a time t, how many houses have they painted in that span of time? How many houses? 2/8. Okay. Well, let's have a look. So it's basically 1/3 times t plus 1/5 times t. And now what were we interested in? How long does it take them to do one house, right? So how can we turn this into an equation that, so we want to find a t, right? So that eventually we get one house. So we'll just put a 1, and then we solve. And when we solve, we get this sort of thing. So what is t? Yeah, that's right. Okay, so let's just see whether they get it right in the movies.
Using the simple formula A times B over A plus B, we arrive at our answer of 1 7/8.
Wow, are you sure?
Oh, but of course, my diminutive leader. Long have I been familiar with the exactitudes of the mathematical world.
So there's somebody who gets it right. Outside the Simpsons. Amazing. So here's something else, and I've actually just used this in a class at Monash. It's called The Nature and Beauty of Mathematics. Marty set this up a couple of years ago that he left Monash, and I inherited the course, and I'm eternally grateful to him because it's my favorite course. We can talk about anything. So, so I actually used this sequence here in a course to talk about something very famous.
Fermat's last theorem. You're familiar with it?
Vaguely. I spent too many math classes daydreaming about being on a starship.
When Pierre de Fermat died, they found this equation scrawled in the margin of his notes. X to the n plus y to the n equals z to the n, where n is greater than 2, which he said had no solution in whole numbers. But he also added this phrase, remarkable proof.
Yeah, that's starting to come back to me. There was no proof included.
And for 800 years, people have been trying to solve it.
Including you.
I find it stimulating. Also, it puts things in perspective. In our arrogance, we feel we are so advanced. And yet, we cannot unravel a simple knot tied by a part-time French mathematician, working alone without a computer.
Captain, we detected some sort of debris in a loose orbit.
Can you identify it?
No, sir. I suggest we beam a section aboard for analysis.
Make it so, number 1.
None of it makes any sense.
Like Fermat's theorem, it's a puzzle we may never solve.
So he talks about a very, very famous result in mathematics, or a theorem which has not been proved. Fermat's theorem, so there's Pierre de Fermat, and he lived 1601, 1665, and sometime during that time he came up with this idea. Well, what does it say? Well, it says x to the n plus y to the n equals z to the n. And he says if n is greater than 2, then you can't find any integer solutions for this. Well, okay, let's have a bit of a close look at this. Let's just have a look for 2. Right? So for 2, so n equals 2. Can you find any x, y, and z so that you actually get x squared plus y squared equals z squared? Does anybody know? Yeah, but I want integer solution, so 3, 4, 5? That's right. So 3 squared plus 4 squared equals 5 squared. Okay, does anybody know any other solution? Say it again. 5, 12, 13, that's very good. There's actually other ones. So for example, we could take 1, 0, and 0. But kind of a bit cheating, okay? So cheating solutions, so we don't use those. But use is definitely, you know, good. So 5, 12, and 13 would work. And actually, always try to actually teach a little bit of mathematics here. So I'm going to try and teach you to find infinitely many ways of filling in those numbers. And it's a very nice little trick. And it's based on this little formula that everybody knows. Everybody knows this? N plus 1 squared is n squared plus 2n plus 1. Everybody seen this? Say no. Okay, so let's just put some brackets here. Let's just put some brackets. Okay, now it's 3 numbers, okay? So it's 3 numbers. There's a square. There's a square. What about this one here? It's not a square yet. We can make it a square, okay? So if you put n equals 1, for example, you get here in this bracket, what do you get? N equals 1, you get 3. And n equals 2? 5. N equals 3? 7. Then 9, then 11, then 13. What do all these numbers have in common? They're all odd numbers. Okay, odd numbers. Okay, so here's the trick. Here's the trick. We have a square. We have another square. And now what we're going to do is we're just going to choose an odd square. What's an odd square? First odd square is? Actually, it's 1, but we don't want that one. Can't do it like this. But 9 is the first one, okay? So we'll just put the 9 there. So which n belongs to the 9? 4, right? So that's 4. Now what we do is we just plug the n 4 in here. So you get a 5 here, it's 5 squared. Here you get a 4 squared. And here you get a 3 squared. So 3 squared plus 4 squared equals 5 squared. What do we do next? We do 25, right? Any odd square here will give you something good. Okay, so we'll just try this. So we'll put 25 here. So what is the n that belongs to this one? We need 2 times that mystery number plus 1 equals 25. What is that? 12. Okay, so we've got 12 here. 12 plus 1 is 13. 12 squared. And here you've got 5 squared. So that's exactly your solution there. And what's the next one? 49. Okay, so 49. So what's the number? 7 squared. Yeah, 24 and 25. So you can actually do this for any odd square. Any odd square via this thing that you know will give you one of those triples of numbers. There's actually infinitely many. I've shown you infinitely many. There's actually even more than this. Okay, so I've just shown you some. So no problem finding solutions for this sort of equation here. But what about if you change the 2 to a 3? Can you find x, y, z so that this is satisfied? We can still go the cheating way, right? 1, 0, 0 will work, but we don't want to worry about cheating ones. And actually it turns out, it's been known for a long, long time, it can't be done. Okay? And what about 4? It can't be done. And actually, Pierre de Fermat, Captain Picard also mentioned this. When he stated the theorem, he also said, I've got a really, really good proof for this, but it doesn't fit here, so I'm not going to say it. And then people actually have been trying to find that proof. And they've been trying, well, what if they succeeded in doing is to say, well, for 3 it doesn't work, for 4 it doesn't work, for 5 it doesn't work. But they could never really do, like, all of them, right? They couldn't do all of them, all n, in one go. So they couldn't do this. And as Captain Picard, when does he live? 200 years in the future, says, it has never been shown, right? So 200 years in the future, they're still trying to figure this out. Now, there's a bit of a problem here, okay? And the problem is that actually in 1993, which is 4 years after this episode was shown, somebody actually found a proof for Fermat's last theorem. So it was a Princeton mathematician, Andrew Wiles. There he is, smiling because he found a proof. Yeah. And so this was a big, big thing. Anybody remember? Like, this going through the news? Yeah? Well, they even made a musical out of it, right? The musical that I mentioned before. Fermat's Last Tango is actually about the proof. And here's basically Wiles summarizing what I just said.
Many square numbers can be divided into two other squares, but according to Fermat, you cannot make it work. So are cubes, or fours, or fives, or sixes, or more. In fact, there are no number solutions where n is greater than 2, not 3, and not 10 million. That is the theorem, Fermat's last theorem, for which I have a proof.
Why is this important? Why is this important?
Won't go into this, okay? But anyway, Martin, I actually once showed this at like the hugest teachers' conference in the whole planet, which is actually organized by the MAV. It was held at La Trobe. It's like an annual event where like 3,000 participants come together to talk about maths. And we showed this in the evening, and it takes about 2 hours. And we started out with a huge audience, and I think by the end of it, we had like 5 people left. Simon was one, Martin was one, me and 2 other diehards. Yeah, everybody else had given up on it. But actually, it's a fantastic thing, so we really recommend that you check out Fermat's Last Tango. Right. Okay, so 1993, somebody actually found a proof. Well, Star Trek actually tried to correct their mistake 2 years later. 1995, had another episode, and here we have.
I've been working on finishing your proof of Fermat's last theorem.
You have?
It's the most original approach to the proof since Wiles over 300 years ago.
Thanks.
Well, so I mean, Star Trek fixed it up, basically. But actually, when Wiles came out with the proof, there were some problems with it. Right? There were some problems with it. So not all people thought that this was actually valid what he had done. And there was a lot of discussion about it. And actually, even The Simpsons got into the picture at some point in time. So here we have The Simpsons.
Man, this place looks expensive. I feel like I'm wasting a fortune just standing here. Better make the most of it. Ow! Watch it, Coney! Oops. It's like, did anyone see the movie Tron?
Well, it looks like Tron, right? But we're not worried about Tron, we're worried about this. This is a counterexample to Fermat's last theorem. This shouldn't exist, right? 1,782 to the power of 12 plus 1,841 to the power of 12 is equal to 1,900 and whatever it is to the power of 12. So, well, what do you think?
Left-hand side's odd, right-hand side's
We're going to check it. We're going to check it. I've got a 1995 calculator, and we're going to check it. Because people these days check everything with calculators. In school, you're not allowed to do anything. If you don't use a calculator, you're out. Right. So, 1995 calculator, let's give it a go. So, 1,782 to the power of 12. Put it to storage. Okay. Second number, 1,841. To the power of 12. It's the good old times here. Put it into storage. And the last one, 1,922. Okay. Now I'm actually going to add up those two and subtract the other one, and let's see what we get. Plus this one. So it's basically the left side of the equation. We minus the right side of the equation. We get 0. Seems to work. So what's going on? What's going on? Is Wiles wrong and Simpsons right, or what? Don't think so? Well, huh? Ah, so you can actually, without a computer, it's actually a good idea to not use a computer for this sort of thing. You can see at a glance that this cannot possibly be true. Have a look at this number here. That's an even number. Even number to anything is still an even number. What is that here? That's an odd number. Odd plus even is odd, right? What have we got on the other side? Even number. So this actually, you know, it's an odd number on this side, an even number on the other side. It cannot possibly be the same. Now I'll actually show you the numbers, okay? So here are the numbers. Those are the numbers. This is the left side. This is the right side. Right? So it's just that the computers, you know, they only can display a certain number of digits. So you go up to here, and then the rest is actually completely different. But it's not picked up by those machines. But this is, of course, done with a modern computer like yeah. All right. So that was. Yeah. That was not the last word, right? So the Simpsons had another idea here. So that was in 1998. They thought they had another example, and you can actually check here. There's an odd number plus an odd number is an even number, and there's an even number. So, you know, so you have to think about it a little bit harder. But you can also show, of course, that it is not true. Actually, with the first episode, they got like zillions of calls from people like myself saying, this cannot possibly be true. All right, so actually, so this sequence here, I've actually just used a couple of weeks ago when talking about Fermat's last theorem. So that works really, really well with students. Okay, and this is one, you know, for a really advanced maths class.
Let me just show you how to construct the math S, which is the fun of the lemma. Anyhow, okay? So you assume you have an element in the kernel of gamma that is an element in C, such that gamma takes you to 0 in C prime. You pull it back to B, like map G, which is surjective.
Hold it. That's not unique.
Yes, it is unique, Mr. Cooperman, up to an element in the image of F, all right? So we fold it back to a fixed B here. Then you take beta of B, which takes you to 0 in C prime by the commutivity of the diagram. It's therefore in the kernel of the map G prime, hence is in the image of the map F prime by the exactness of the lower sequence. So we can pull it back to an element in A prime.
It's not well defined.
Which it turns out is well defined modulo the image of alpha. And thus defines an element in the co-kernel of alpha. And that's the snake. And on Monday, we'll address ourselves to the cohomology of groups and Mr. Cooperman's next objections.
Anything wrong with this? Anybody notice any problems with this? No? There's actually no problems with this at all. It's amazing. So you can just play the clip, sit back, and have the class taught by Hollywood actor. It's fantastic. But I've actually talked to the person who advised on this movie, and he told me she didn't understand anything she's saying here. So she really learned this text here like she would learn Chinese, which she didn't know either. So syllable by syllable, basically, and it took her a long time. And then, well, pretty good performance. It's actually a movie with Michael Douglas and, what's her name? Jill Clayburgh. Right? It's My Turn from 1998. So, I've used that before. So that's actually algebra, if you do. So it's not the algebra you see in school, that's algebra you see at the university. So this is a very important question to answer, and movie clips are great for this one, so I'll just show you a couple. So when is mathematics of any use to you?
10,000, 12,000, 15, 16, 17, 22, 22.
Any trouble, boy?
No, old man. Thought I was having trouble with my adding. It's all right now.
Next one.
Martha, Riley, how you doing?
Area 29 and North 28.
Yeah, you gotta move faster.
We're doing our best.
Find the next number in the sequence. 313? 331, 367.
What? You said the crew knew all the answers.
The crew's changed as we set the questions.
You're joking.
379.
What?
It's a sequence of Happy Klein. 379.
Happy
Just enter it. Are you sure? We only get one chance. Any number that reduces to 1 when you take the sum of the square of its digits. The continuous arithmetic yields 1 is a happy number. Any number that doesn't isn't. A happy prime is a number that's both happy and prime. Now type it in.
Oh, I don't know. Talk about dumbing down.
Don't they teach recreational mathematics anymore?
So this is really saving, saving half the planet, okay? So the first one was kind of just saving yourself, so saving half the planet. This is saving Starfleet.
The computer will not respond to these controls. The entity is unquestionably controlling it.
And the computer controls the ship. Spock, don't you have a compulsory scan unit built into the computer banks?
Yes, we do, Captain, but with the entity in control.
Well, aren't there certain mathematical problems which simply cannot be solved?
Indeed. If we could focus the attention of the computer on one of them.
That ought to do it. Implement.
Computer, this is a Class A compulsory directive.
Compute to the last digit the value of pi.
Okay, here's one more. So this is to save yourself, yeah. So the most important one, probably.
What if I did something embarrassing to myself? Would that make you feel better?
There's nothing you can do that would be this embarrassing.
I fear that I will always be a lonely number like root 3. A 3 is all that's good and right. Why must my 3 keep out of sight, beneath a vicious square root sign? I wish instead I were a 9, for 9 could thwart this evil trick with just some quick arithmetic. I know I'll never see the sun as 1.7321. Such is my reality, a sad irrationality. When hark, just what is this I see? Another square root of a 3 has quietly come waltzing by. Together now we multiply, form a number we prefer, rejoicing as an integer. We break free from our mortal bonds, and with a wave of magic wands, our square root signs become unglued, and love for me has been renewed.
So all these things come in handy at some point. Okay, so actually we're kind of getting towards the end here, so just quickly, I want to give you a little bit of a behind-the-scene look to some of this stuff. So this is actually the table of contents of our book, and like the first half is all about particular movies like Good Will Hunting and Beautiful Mind, all sorts of other things like the 7x13 trick. Here it's all about themes, so like infinity and visualizing higher dimensions and all sorts of other things. Let's just play 3 clips. We're running a little bit out of time, so I'm going to play them simultaneously, which is going to be interesting. They all have something in common, so you tell me what they have in common.
No, I was hoping for a kiss.
Well, why don't you just get out of the way now?
Yes, tell me how. Now, y'all. Don't forget the coffee.
Oh, shit! You didn't say that.
For Christ's sake, buddy, it's a joke.
And if something actually happened to him,
A joke?
looks right.
So what do all these 3 scenes have in common? One thing is easy, it's kind of highlighted out there. So they're all from the movie Good Will Hunting. The other thing, which is not so obvious, is they all have a real mathematician in them. So the first one is the one walking there. That's what's his name? Kleitman. He's a professor from MIT, so the director actually talked to him first when he had the idea for Good Will Hunting. And so he got a bit of an appearance there, just the background. Now this one here is John Myton, who was a PhD, they shot the movie at Toronto, University of Toronto. He was a PhD student in physics and mathematics, and he's now a PhD in mathematics and is running a special program for people struggling with mathematics in Canada. He's also a very successful playwright, but he's a real mathematician. And this was actually the main advisor for the movie in terms of mathematics. That's Patrick O'Donnell, and he's a professor at physics actually was. He just died a couple of months ago. And we actually talked to people like this to make sense of what's happening in terms of maths in the movie. So We have a long interview about Good Will Hunting with this, and I just have a little bit of a clip from this for you. So this is Patrick O'Donnell, and here's him and me doing an interview over the phone, talking about Mads and Good Will Hunting.
So then I had a script, and they had one scene. The one thing I found about Hollywood is that none of the actors could write on a blackboard. Not at all. So in fact, all the writing you see, essentially all the writing, maybe one wasn't quite, but is mine.
Okay.
Because in fact, they did some of it where it really was not really appropriate because there was too much of them. They were supposed to write in 17. In fact, we were invited to New York to the premiere. My wife had seen the dailies in one of the scene I am the actor in, but we'd never seen the rest of the movies. And she said to me at one point, she said, this is terrible. She says, I see your handwriting everywhere, but somebody else is finishing off. And in fact, there is one scene where it wasn't written in the script originally, but they got to MIT, and so I guess it's two postdocs coming up the room, and there was a board in the corridor, and one wrote something and the other wrote something, and they didn't speak. They were communicating through the equations, whatever they were doing. So he wanted a scene like that, and I said, well, just do it the way they do it. Well, first of all, by the time the movie was going to shoot that scene, I then had realized that nobody could write. So I had to dumb it down and dumb it down and dumb it down. All they had to do was score out. I think it was something with factors, one over the other. I forgot what it was now.
Yeah, so we did a long interview about this, and this is all his writing, like all his writing. And basically, the only thing he could really do was kind of do a stroke here, right? So talking at the same time and doing something on the blackboard is completely impossible for actors in Hollywood. And that was kind of a common remark that everybody I talked to, and Marty talked to, made. So none of the actors, like Russell Crowe, couldn't do this. Right? They were just in awe of all the mathematicians could do, and all the teachers, I guess, who could write on the blackboard and act at the same time. Anyway, I could really talk a lot about this, but we're kind of getting close to the end of this. So I'll skip to the next bit and maybe the next bit. Just talk about something, so we have this huge list that's been out there for a long time. And once it's out there for a long time, and people actually start noticing it, and they approach you about maybe helping out with the movie. It also happened to us, Marty and me. So we actually helped out with the episode of City Homicide. Did anybody seen City Homicide? It's an Australian detective series. And so they wanted to murder some mathematicians and they needed some help with that. So we were happy to oblige. We felt like in a murderous mood that week anyway. And so here's a mathematician that gets murdered, and actually they get murdered and found with all sorts of mathematical writings all over the bodies. And actually this was Marty and me writing with tattoo pens on the bodies. And like all the blackboards and all the other things that you see in the movies, everything has something to do with mathematics. It was actually us doing it. So there's a couple of blackboards here in the background. And we tried to fit as much nice mathematics in as we could. There's a very famous Formula One here. And there's another one also very famous here. We even got this one here in. So if you watch very careful, you actually find our logo. So the QAD cat lurking there at one of the shots. So Marty thought I should put it in anyway. It was really, I even had the murder weapon. That's the murder weapon here. So that's one of my props at Monash. So you can see there, it's the murder weapon here for one of the bodies. And it was just fantastic. What a lot of people, like also Patrick O'Donnell does when they get asked for help with movies, we try to put some really interesting bits in. So I've got the sieve of Eratosthenes in here, and the golden ratio, and this really, really famous equation, and all sorts of other things. And there's Marty in action putting one of those things together, and I think we spent a whole night doing this. All right, now let's just have a look at how we go. Oh yeah, right on time. So I think what I'll do now is just stop here, Now, if you want more information about any of this, if you want to have a look at the book, for example,